Hi students, and welcome to the lecture video on chapter 4, Alkanes and Cycloalkanes, part 1. Okay, so we're going to start off talking about alkanes. And one of the definitions that we want to know is on the definition of a hydrocarbon. And a hydrocarbon is just a compound that's composed of only hydrogen and carbon. And all of the structures you see on this slide are examples of that. But some of them are considered saturated versus unsaturated hydrocarbons. So if you see one or more pi bonds, then we consider that structure to be unsaturated because it does not contain as many hydrogens as is possible for the number of carbons without breaking any carbon-carbon bonds. Whereas alkanes would be considered saturated because they are saturated with the maximum number of hydrogens possible. So those are just some definitions to be aware of. Again, there's a pi bond, at least one, we would call it unsaturated. If there isn't, then it would be a saturated hydrocarbon. And we're going to start talking about how to name alkanes in this chapter. The process of naming compounds is called nomenclature. You probably learned a little about nomenclature in general chemistry when you learned how to name different ionic and also covalent compounds. So we're going to be also talking about naming primarily organic compounds this year. And it starts off in chapter 4 with naming alkanes and cycloalkanes. And then nomenclature continues in a lot of the subsequent chapters after this by including various functional groups. So for example, eventually we'll learn how to name haloalkanes and alkenes and alkynes and so on in subsequent chapters. And the rules just sort of build off of the rules of naming simple alkanes. So before we start talking about naming alkanes, let's talk about the fact that you may have heard some compounds being referred to by what we call common names. So for example, these are all compounds that have been named using a common name. So for example, this is formic acid, and it's isolated from ants after the Latin word for ant, which is formica. We have urea, which is isolated from urine. Morphine, which you guys know is a painkiller. And it's actually named after the Greek god of dreams, Morpheus. And then another example would be barbituric acid, which Bayer named after his wife. Actually, it doesn't say his wife. Okay, sorry, just a woman named Barbara. So you can see that common names can be derived from anywhere. They could be derived from the substance with which the compound was first isolated. It could be named after, things like Greek gods, or even named after random people in honor of those people. So you can imagine with, millions of different compounds that are possible, particularly compounds that contain carbon, because carbon is so versatile, making so many different types of covalent bonds. We can't memorize millions of different names that are derived randomly. And so we have to learn how to name things systematically. And so we're going to learn the IUPAC system of nomenclature. And IUPAC stands for the International Union of Pure and Applied Chemistry. And they've come up with a systematic way of naming compounds. And so we're going to follow a systematic, which means basically stepwise approach to how to name compounds. And there's different steps involved, but the system includes identifying what's called the parent name, which is the longest carbon chain, and then naming substituents, and also what we call the location of substituents, which is the numbering system or the locant system. So the first step is identifying the parent chain, right, which is the longest consecutive chain of carbons. So you can see here, if we were given this structure, it wouldn't be necessarily immediately clear where the parent was. We might have to do some counting. So for example, I could start here and go, okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, right? And so on. And what you would eventually come up with is there will be a longest carbon chain, and that's going to be the parent chain. This parent has 9 carbon atoms. What if there's more than one possible parent chain? So for example, let's say you count 2 different ways and you get the same number of carbons. For example, the structure here, you could count in this direction and get 7 carbons, and then another direction and get 7 carbons. So which one is the correct parent? Well, in a case like that, we need to choose the one with the most substituents attached. So for example, if we counted in this direction, and by the way, I'm sort of going from top to bottom, but it could be bottom to top. Right now, it doesn't matter. But if you count along this red path, right, we get 3 substituents versus the other path would only give us 2 substituents. So when there's a tie for the parent, go with the one with more substituents, greater number of substituents if possible. And then in order to name the parent, we need to know some roots that we're going to use for the naming system. So what you want to know is the root of the word, right? And then they'll always end in the suffix -ane. So for example, if it was only 1 carbon, the root would be meth, and we would call it methane. And so on. So if there's 2 carbons, right, it becomes ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. And it goes even further. However, you're only going to be responsible for memorizing the first 10 parents or roots, really, of the parent. So maybe make some flashcards and commit those to memory quickly. However, I will say if you're doing enough practice problems, you have this chart handy with you, eventually you will just know them without spending any time memorizing them, just because you've done enough practice with nomenclature. Okay, what if the parent chain is a cyclic alkane? If that's the case, then we're going to use the prefix cyclo in front of the rest of the parent name. So for example, if it was 5 carbons, we would normally call that pentane, but because it's a ring, we call it cyclopentane. Let's practice the skill and practice identifying and naming the parent of each of the following compounds. So go ahead and pause and then come back in, and you can work on finding the parent, and then we'll go over the answer. All right, I'm going to assume that you have worked on this by yourself. We'll go ahead and go over it. If I can get that a little more in focus. Good. Okay, so here, right, we might want to start doing some counting. We go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So that is the longest possible path, right? 1, 2, 3, 4, of course, would be much shorter than that. So we can sort of, you could maybe highlight it or take a pen and circle it, right? And we have, so I said it was 6 carbons, right? 1, 2, 3, 4, 5, 6. So this becomes hexane. Let's start doing some counting over here. So here we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Uh-oh, there's a tie, right? There's 2 different ways to get 7. We either sort of count in a left to right on the horizontal fashion, or move down, right? This would be 1, 2, 3, 4, 5, 6. So that's not as long. So there's 2 different potential ways, right? We could either go this direction or this direction. So if we go from here to the bottom, we would only have 2 substituents. But if we go from left to right or right to left, we end up with 3 substituents, these 2 branches and this one down here. So this is in fact correct parent. Right, and we said that had 7 carbons, so that's going to be a heptane. Right, and then I'll just make a note, right, choose the parent with greater number of substituents when 2 paths have the same number of carbons. Just a little note, just in case somebody ends up picking the wrong one. And then here, right, if we count the carbons outside of the ring, it's only 1. And then inside the ring, it's 1, 2, 3, 4, 5, 6, 7. So some people might wonder, can I do like the 7 in the ring and then also go outside of the ring, continuing the path? And the answer is no. So carbons are either part of a ring or outside of a ring, right? They can't, a parent can't contain both. And so what we'll end up doing is just taking the carbons that are part of the ring, because that is the longest path, right? And this will be, don't forget the cyclo, because of the ring, right? Cycloheptene. All right, coming back to the slide, we're moving on to naming substituents. So the second step after we've identified and named the parent is to identify and name the substituents, which are the carbon-based groups that are attached to the parent but are not part of the parent. So for example, we might have already identified that this is the longest carbon chain, which is the parent, right? And then the other carbons that are attached to that must be the substituent. So there's 3 substituents here. And the way they get named actually uses the same roots to the words that we were using for the parent, but instead of the suffix ane, they contain the suffix yl. So if there is a substituent with only 1 carbon, we call that a methyl group. If it contains 2 carbons, it would be an ethyl group, and then 3 carbons would be a propyl group, and so on. So there you can see the names have been added, methyl, ethyl, and propyl, noticing that the suffix YL is used instead of ANE for substituents, which was different from how we named the parent. Okay, what about a ring? A ring can either be the parent chain or it could be a substituent depending on the number of carbons. So again, the parent is the longest carbon chain, and that can either be a ring or it could be carbons outside of the ring, whichever is a longer number of carbons. So for example, in the case where we have this structure, we've got 3 carbons that are outside of a ring and 6 carbons inside of a ring. So that means that the parent is the ring, and the parent is named cyclohexane. Notice that the substituent is named propyl because of 3 carbons with the ending YL. In this case, though, it's a smaller sized ring, only 3 carbons, and the number of carbons outside of the ring is 4. So the straight chain carbons actually ends up being the parent, and the ring is the substituent. So the parent is butane because it has 4 carbons, and the substituent then becomes cyclopropyl. And notice this one is what we call a locant, which is part of our numbering system, which we'll explain in a little bit. Okay, before we do that though, let's talk about naming complex substituents. So sometimes, for example, there can be a substituent that has branching on it. So we need to know, how do we name that in a systematic way? Well, the steps to naming a complex substituent, which means basically a substituent where all the carbons are not attached linearly, but there's branching. You're going to start numbering the substituent. Numbering number 1 will be the carbon attached to the parent, and find the longest carbon chain possible for the rest of the numbering. So the longest carbon chain within the substituent in this case is 4 carbons long. So we would name that a butyl. But it also has this branch attached, right? And that branch is attached at carbon number 2. So this becomes what we call a 2-methyl butyl, right? So think of it as like a substituent on the substituent. And because they're both substituents, they both get the YL, which is why you see the methyl butyl, right? And the number just tells us where we can find that methyl, because it would be different if it was on carbon number 1 versus carbon number 3, right? Or so on. And also the complex substituents, because they have numbers associated with them, they go inside of brackets. And as we do more examples, it'll become obvious why it needs to go inside of brackets. And the reason really is, though, there's going to be numbering associated with the parent, and now there's also numbering associated with the substituent. So that becomes a little confusing if you don't use brackets. So numbers inside of brackets refer to branch points attached to a substituent, and numbers outside of brackets mean it's the numbers associated with the parent. And again, you're going to need to do some examples probably to fully understand that concept. But before we do that, we want to talk about some complex substituents that also happen to have common names. And that's because they're common groups. They just happen to be complex substituents. So that means that they have both a systematic way of naming them, like we just talked about with the 2-methyl-butyl, but they also have a common name that we can use instead of the systematic name. So oftentimes there's more than one way to name something, especially if there's a common name involved. And again, why do we use common names instead of the systematic way? It's just because people have been naming compounds long before there was a systematic method for naming compounds. And so these common groups have got common names that just appear in old literature. And it's important that chemists know what those mean because they were named before the systematic method of naming came into be. And so chemists basically have to know how to do it both ways. And so we accept, IUPAC essentially accepts these common names even within its method of nomenclature. Okay, so if you think about it, there's more than one way to attach 3 carbons to a parent. It's possible that all 3 carbons might be attached, right, linearly, in which case it would just be a simple propyl group. But what if those 3 carbons were attached at the center carbon, right? You would still agree that this is 1, 2, 3 carbons. It's just not attached at the end carbon. Now it's attached at the center carbon. So this, if we were naming this systematically, would be a 1-methyl ethyl, but it also has the common name of isopropyl. We can use either one. And next we have the butyl group, right? So if you had simply 4 carbons in a row, it would just be a simple butyl group. But there's other ways to attach 4 carbons. And as you might imagine, that with the more carbons, there's going to be more possibilities for how those carbons might be attached to a parent. But there are multiple ways that are considered common. So for example, we have, instead of being attached to the parent at one of the terminal carbons, if it's attached at one of the internal carbons, then we have a name for this called sec-butyl. By the way, the sec stands for secondary. And what it refers to is the fact that this carbon, while also attached to the parent, is attached to 2 carbons. And so that's where it gets the secondary or 2 from. And of course, there would still be a systematic way of naming this, which you would number 1, 2, 3, and then this would be a 1-methylpropyl group. Do you remember the little antennae for isopropyl? Well, that still comes in for a common name with the butyl group. So if you kind of imagine the little antennae with 4 carbons instead of 3, instead of isopropyl, it becomes isobutyl. And again, the systematic way of naming that would be in parentheses 2-methylpropyl. And then we have the carbon where all 3 carbons other than the initial carbon are attached to it, with 4 carbons total. And because this would be a carbon with 3 carbons attached, not including the parent, we would name this tertiary or tert butyl. And the systematic way would actually be in parentheses 1,1-dimethyl ethyl. And this di refers to the fact that there's 2 methyls, right? And there's 2 numbers that tell you exactly where those methyls come. So if we had named this, the numbering would be 1, 2, hence the ethyl as the primary longest carbon chain on the substituent. And then 2 1-carbons attached to that, 2 methyl groups attached to the ethyl, right? Each one at carbon number 1, so it becomes a 1,1-dimethyl ethyl. And then there's actually lots of different ways of attaching 5 carbon atoms to a parent, but only a couple of those have common names. So of course, the simple way would just be all in a row, and that would just be a pentyl group. But we also have, remember the antennae, those are very common, right? So in a 5-carbon chain, we have isopentyl. Some people will also call this isoamyl. And the systematic name would be 3-methylbutyl. And then if you have think of it as the chicken foot, right? The chicken foot last time was called tert-butyl with 4 carbons. And now it's going to be called, instead of tert, because it's not the carbon directly attached, it's not going to be a tert, but it'll still have a neat name and it'll be called neopentyl. And again, systematic would be 2,2-dimethylpropyl. So again, there are other ways of attaching 5 carbons that are in a complex way that are not these 2, but these are the only 2 that have common names. The other ones you would have to name via that systematic way with the parentheses. Okay, so let's talk a little bit more about numbering, because we've kind of alluded to numbers within the substituents, right? And it's also important to number the parent and not just the complex substituents. So when we're numbering the parent, we want to, of course, number all of the carbons in the parent or the longest carbon chain. And there's usually 2 ways to do it. You can start from one side and go to the other, or start from that side and go back. And you would want to do so in such a way as to get the lowest number possible for any substituents, or the first substituent that you might see. But also, it's important to recognize that numbers are important because they tell us where substituents come. So for example, on this pentane, it's possible to have a methyl group at carbon number 2. It's also possible to have a methyl group at carbon number 3. And if we named those both methyl pentane, then it wouldn't be clear which one we're referring to, right? If I said, oh, the compound is methyl pentane, you might draw this and somebody else might draw this. And as you know, these 2 compounds are related as constitutional isomers. They're not identical compounds, right? They have the same molecular formula, but they have a different atom connectivity. Therefore, they are not identical, they're different, and so they have to have a different name. If they don't have a different name, we wouldn't be able to distinguish between them. So that's where that numbering comes in, right? And we would name this 2-methylpentane versus 3-methylpentane. And again, you might be thinking, well, if I had numbered from this direction, 1, 2, 3, 4, 5, then wouldn't it be called 4-methylpentane? So remember that you want to assign your locants such that the first substituent, in this case there's only one, but sometimes there's more than one, the first substituent would get the lowest number possible. So there is no such thing as 4-methylpentane. It would be named 2-methylpentane. Okay, and so this is where we're talking about that. Which way do we number, right? Do we number? There's multiple ways that you could count or number a parent. And again, we want to do so where if there's only one substituent, it should have the lowest number possible. What if there's more than one substituent? Well, in that case, you want the lowest number possible for the first substituent. So for example, if I was to number from left to right, I would end up with 3 methyl groups, and those would be at 2, 5, 5. And from right to left, it would be 3, 3, 6. So we just look at the first number, and we want the lowest number possible. So 2 is lower than 3, so this is the correct way. Notice how I didn't consider the fact that 5 was greater than 3, right? We're only looking at the first number or the lowest number, and that's going to be our first tiebreaker. But sometimes if you do that, you'll end up with this, the first number will be the same. And in that case, you would go into the second number and say, okay, I want the lowest number possible for that number, and so on. Sometimes you can number a parent 2 different ways, and you can get this, there's essentially no tiebreaker that you can come up with for getting the lowest number possible. So for example, if I was naming this alkane, by the way, we won't really talk about halogenated alkanes nomenclature in this chapter, but they just use this example early just to illustrate the difference or the next tiebreaker in terms of assigning locants to the parent. So if you were to number from right to left, you would come up with a substituent at 1 and a substituent at 5. And from left to right, there would still be a substituent at 1 and a substituent at 5. You can see that 1, 5 and 1, 5 is a complete tie. And in that case, you would look at, okay, what exactly are the substituents, right? For example, when we learn how to do this, we'll learn that this is named bromo and this is chloro. And then we'll look at alphabetical order, and the first to come in the alphabet will get the lower number. So for example, because B comes before C in the alphabet, we'll end up calling this 1 bromo, 5 chloro, as opposed to 1 chloro and 5 bromo. And the same rules apply for cycloalkanes. So the thing with a cycloalkane is you could start anywhere in the ring, right? I could start counting here or here or here, anywhere, right, in this 6-membered ring. But I want to start at the position that will give me the maximum number of substituents with the lowest number. So for example, I would think either I should start here because there are substituents at this carbon, or I should start counting here because there's a substituent at this carbon. And those 2 methods are shown here. And again, look how you can go for clockwise with your counting or counterclockwise with your counting, and that doesn't matter. But this would be the correct way because we would get substituents at carbon 1. There's a second substituent at carbon 1, and then the third substituent at carbon 3. So 1, 1, 3 beats 1, 3, 3. So how are we going to assemble the complete name of a compound, right? So the parent name always goes last in the name, and before the parent, we list substituents. And those substituents are listed in alphabetical order. They also include numbers, but we don't go in number order, we go in alphabetical order. And I know that's very confusing, but that's why it takes practice to really get used to exactly how to do this. So again, the parent goes last. All of the substituents to the parent go before the parent in alphabetical order. You include the numbers associated with the parent or complex substituents, but we don't go in number order, we go in alphabetical order. When we're thinking about alphabetical order, it's going to become important to understand what counts in terms of alphabetical order and what doesn't. So all of the roots that you learn, like M for methyl, right, and E for ethyl, those count. But when you have prefixes that are used because there are multiple groups that are identical, those prefixes don't count. So for example, if I was alphabetizing ethyl and dimethyl, right, I'm going to use the E from ethyl and the M from methyl, not the D from dimethyl, right? So the D in di doesn't count. You then go to the M for methyl. So what we call counting prefixes, like di, tri, tetra, penta, and so on, counting prefixes, because there are multiple of the same group, those don't count. Other counting prefixes are from those common substituents we talked about, like sec-butyl and tert-butyl, right? This S and the T are considered counting prefixes, and those don't count towards alphabetical order. However, remember iso, right? Iso or neo, the I and the N, those are not considered counting prefixes. And so those would count in the alphabetical order. Another thing that does count in alphabetical order is the C for cyclo. Cyclo is not a counting prefix. Okay, so the general pattern that you're going to use when you're working on these problems is to first identify the parent chain, which again is the longest number of consecutive carbons, either inside or outside of a ring, and then name it. We want to identify and name the substituents. And by the way, steps 2 and 3 are often reversed. Like I like to do step 3 before I do step 2, but that's optional and can depend on who's doing the problem. So in either order, you want to identify and name the substituents and number the parent chain to assign a locant to each substituent. And then put the whole name together by listing the numbered substituents before the parent name in alphabetical order. So that's a lot of explaining, but really the best thing to do is do lots of problems so that you see all the rules sort of come into play. Let's go over an example, right? Let's say we were naming this compound. What we'll see is that the longest carbon chain is actually the ring, right? So the parent name is going to be cyclohexane. And then I like to, as my second step, assign the locants to the parent chain. So I know that cyclohexane is my parent, and I want to count from 1 to 6 then on the parent. Remember that with a ring, you can kind of start anywhere, but you want to do so to give the lowest number to the first substituent, which could of course be here, 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 but if you start here, then you get the lowest number for 2 substituents, which is the best. So then we have 1, 1, 3, 4, which would beat any other pattern. Like if I started here, it would be 1, 2, 4, 4. Or if I started here and went this way, it would be 1, 2, 5, 5, and so on. You'll see that 1, 1, 3, 4 gives us the lowest possible early numbers. Okay, and then as soon as I've assigned locants, I want to name all of the substituents. So with just 1 carbon on these first 2, both of these are methyls, right? So there's 2 1-methyls, and we just combine those into 1, 1 dash dimethyl. That's where that counting prefix comes in when you have identical groups. And then at carbon number 3, we see we have 2 carbons attached, so that's a 3-ethyl. And at carbon number 4, this is a complex branched substituent, but there is a common name for this one. This one is called a tert-butyl group. So we can use either the common name or the systematic name, and I encourage you to use the common name when possible. So then this becomes a 4-tert-butyl. And then how is that put together to determine the final name? Well, recall the parent is always going to go last. We're going to put the substituents before the parent in alphabetical order, regardless of what number they have associated with them. So now we're comparing the alphabetical order. And remember that T is a counting prefix, so that doesn't count. So B versus the E in ethyl. And then down here, the D does not count because it's a counting prefix, so we go to the M. So really it's B, E, M, and that's the correct alphabetical order, which is why we do 4-tert-butyl first, followed by -3-ethyl, and then -1,1-dimethyl cyclohexane. So notice that the substituents are all separated by a dash, but the last substituent directly goes right into the parent without another dash. Let's go ahead and practice this now. I would encourage you to pause the video and go through the steps to come up with a name for each of these compounds. When you're ready, you can resume the video and we'll go over it. All right, let's go ahead and go over this. So we have, right, following the rules, we can name the following compounds. So again, what's the first step, right? The first step is to identify the longest carbon chain, which we call our parent chain. So we can sort of do some counting, right, to figure that out. And we have 1, 2, 3, 4, 5, 6, 7. That will be the longest carbon chain. And then, so I'm going to write step 1. My parent had 7 carbons, so it is heptene. All right, step 2, I like to do step 3 as the second step, which is to assign a locant to each carbon on the parent chain. So I can either start counting here or I can start counting here. So if I do that, I have 1, 2, 3, 4, right? And I have 2 groups at carbon 4, 5, 6, 7, or I could do 1, 2, 3, 4, again, 5, 6, 7. So in that case, it doesn't really matter which direction you go because both substituents are going to be at carbon number 4 regardless. So basically there's symmetry making it so it doesn't matter. So you just go ahead and put it in whatever way, count it either from left to right or from right to left. In this case, it doesn't matter, right? And then we identify and name our substituents. In our substituents, we have this one and this one. So we have 4-methyl and 4-ethyl. And then we want to put this all together in alphabetical order. Notice that we're going to be comparing M and E comes first. Right? So the name of this one will be 4-ethyl dash 4-methyl. And then again, no dash. We immediately write heptane after the last substituent. All right, so we're going to do the same process for here. We're looking at carbons inside the ring. There's 5. And just from a quick look at this, I can tell there's more carbons outside of the ring than inside of the ring. So it looks like this ring will become one of our substituents. So let's start counting. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So the longest carbon chain possible is the 7 carbons in a row here. So again, we could either go with our numbering. Actually, let me just go ahead and write the parent first. So we said again it was going to be 7, right? So it's heptene. We want to put in the numbers. So I could go 1, 2, 3. So substituent at 3, 4, and 5. And then if I go this way, we have a substituent at 3, 4, and 5. That's a total tie, right? So then we consider, okay, what about the names of these, right? So this would be, because we have to go to alphabetical order, and the locants from both directions are a tie. Then I'll go ahead and write in the name of all of these substituents. So this one is cyclopentyl. Right, this is methyl. And then this is isopropyl. And that was a common complex substituent. So if I'm going this direction, right, we have a C versus the other direction would have been an M. So we are going to go in this direction. This is 1, 2, 3, 4, 5, 6, 7 for the locant. Okay, and then we can go ahead and put in the numbers though. So now this becomes a 3-cyclopentyl, 4 isopropyl, and 5-methyl for the substituents. And then the name, right? We have all of our, we have our parent name, we've got our substituents named with their numbers. And so we just need to put this now in alphabetical order. So we have C, next would be I, and then last would be N. So 3-cyclopentyl, -4 isopropyl, -5-methyl heptene. All right, moving on to the last one here. If we count outside of the ring, we only have 1, 2, 3 is the longest chain outside of the ring. So clearly the ring is going to be the parent. Right, so our parent, we'll write it over here. In this case, is going to be, don't forget the cyclo because it's a ring. Right, this is a cyclooctane. There are 8 carbons in the ring. And now we want to do locants, right? So where should I start? Remember, with the ring, I could kind of start anywhere. I want to start at a carbon that's going to have a substituent, of course, because I want the lowest number possible for substituents. And if I start here, I will have a group at carbon number 1, but then I won't have another group for quite some time. That'll have higher numbers. So if I start here, I could have a 1, 2, 6, right? And if I go start here, it would be a 1, 2, 5. So 1, 2, 5 is going to be the lowest number possible. Right? So those, we can put in the other numbers if you want. Right? Those are the ones that have substituents attached to them. Those are the important ones. Okay, so what are the name of these substituents then? Right, well, remember that we have a 1-methyl and a 5-methyl, right? So these come together to become 1, 5, 1, 5 dimethyl. And then at carbon number 2, we have a complex branched substituent. So hopefully you might remember. So first you want to count the carbons. 1, 2, 3, 4, 5. This is one of my pentyls, right? Because it has 5 carbons. And if you remember the little chicken foot, right? The pentyl, it's called neopentyl. So 2 neopentyl. Right? And then we want to think about when we're alphabetizing what counts and what doesn't count, right? So the D does not count because it's a counting prefix. So if you're comparing the M to the N, neo is not considered a counting prefix, so it does count, right? But if we remember our alphabet, LMNOP, right? That's what I always remember. M comes before N alphabetically. So we will put this together. We will say 1, 5 dimethyl -2 neopentyl, and then cyclooctane for the parent. Okay, hopefully you did okay there. And If not, just make sure, and even regardless, even if you did do well, make sure you're doing lots of practice problems. You should have the book, right? There's tons of practice problems in the book. You should always be following up all of your understanding of these concepts, not just with the activities that I assign, but also with book problems. Okay, let's talk about naming bicyclic compounds. So it's possible that there's carbon chains where there's multiple fused rings, and having two fused rings is really common. And so because of the fused nature of the rings, it becomes a little bit harder to name these, right? Because this looks like, is this a 6-membered ring? Is it a 5-membered ring? Is it 2 5-membered rings, right? How do we name this? So we're actually going to name this as what we call a bicyclic compound, and the word bicyclo, or the prefix bicyclo, gets incorporated into the name when you have a bicyclo structure. Okay, some important terminology to know for naming bicyclic compounds. We need to identify the two bridgeheads, right? So there's going to be 2 carbons that are points where the rings are fused, and those are going to be called bridgehead carbons. And then when we are counting for locants, right, we're going to be counting the sort of what we call the bridges that connect the bridge heads, right? So for example, in this case, if you don't count the bridge heads, you have these 2 carbons that are attaching the bridge heads to the left, 2 carbons that are attaching the bridge heads to the right, sort of 1 carbon that attaches the bridge heads pointing up. And so those numbers, right, go inside of brackets, become bracket 2.2.1, which refer to length of the bridges attaching the bridgehead carbons, not including the bridgehead carbons. And that goes in between the prefix bicyclo and the root, which is heptene. Where does the heptene come from? Well, it comes from the fact that there's a total of 7 carbons in this structure. So it becomes a bicycloheptene, but just bicycloheptene is not enough to understand exactly what the structure is, because this is another possible bicycloheptene that actually has different atom connectivity. If you notice, the 2 bridgeheads here have different sized bridges attaching them. In this case, we have a 3-carbon bridge and then 2 1-carbon bridges. So this one would be named bicyclo 3,1,1 heptane versus 2,2,1 heptane, which are different structures. One thing I will point out is that when you're using these, there's no dashes, right? These are not parentheses, they're brackets. They are separated by periods, and we count from largest number to smallest number. And it is possible to have a 0 for one of these numbers. And we'll look at what that would look like. Okay, so let's see. So numbering, right? So we figured out by the way, that whole thing that we just talked about on the last slide is the parent. The bicyclo with the numbers and heptene, right? That's the parent. So now, what if there's a substituent attached to the parent? For example, a methyl group, right? You can see here. So that would need to go into the name as well. In order to figure out the locant associated with that methyl group, we need to know how to number bicyclic compounds. There are 2 rules that you have to follow when numbering bicyclic compounds. You have to start numbering at one of the 2 bridgehead carbons. Notice that they started counting, in this case, on the back bridgehead, and in this case, on the front bridgehead. Both of those match that rule, right? They did start counting. Number 1 was at a bridgehead carbon, so that they have done that correctly in both cases. The next rule is you must count along the longest path, followed by the second longest path, etc. And then, while making sure to follow both of those rules, you want the lowest number possible for the substituent. So you can see here in the incorrect way, they actually followed the rules, but just didn't get the lowest number, which is why it became incorrect. They started at a bridgehead, They counted along the longest path first, right? So this was the longest bridge between the two bridgeheads is going this direction. Then they went along the second longest bridge next, which is going this direction and not going up, right? And then only once they got here did they skip carbon number 1 to get to the next number. So the parent, by the way, in both of these would be bicyclo, and the numbers in brackets, right, would be 1, 2, 3, 4. So 4, 2, 1. So bicyclo brackets 4 period 2 period 1 close brackets. And then there's 9 carbons in the bicyclic ring structure, so it's ends with noning. So bicyclo brackets 4.2.1 close brackets noning. Okay, so which counting is correct, right? Well, this also starts at a bridgehead, goes along the longest path first, followed by the second longest path, and then jumps carbon number 1 to get to the third longest path. And in so doing, it came up with a lower number for the substituent. So this is correct, and we would name this 7-methyl bicyclo brackets 421 close brackets nonane, as opposed to 8-methyl. Let's go ahead and practice by naming the following compounds according to that systematic method. Go ahead and pause, and then when you're ready, come back and we'll go over it. All right, let's go ahead and go over how to do this. All right, so following the rules again, right, we want to name the parent. And this is a bicyclic compound, so we're going to do bicyclo, right, with some brackets, some numbers inside them. And then if we count the total number of carbons in the bicyclic structure, we have 1, 2, 3, 4, 5, 6, 7, 8. Right? So this will be octane. For the numbers, right, I am going to start at one of, think about the bridgeheads, right? Do the longest path first, so 1, 2, 3. That will be my first number. And then 1, 2, and then just 1 up here. All right, so that is the parent. And then, right, the substituent is, of course, a methyl group. But what is the locant for that methyl group? What is the number associated with it? Right, well, we have to start at a bridgehead, count along the longest path first, followed by the second longest path, and then jump to the third longest path. So our options are starting from the back bridgehead and going this direction to come up with an 8 there. Or I could also optionally have started on this bridgehead. I still need to count along the longest path first. So 1, 2, 3, 4, 5. I have to go on the second longest path next. So 6, 7, then I skip 1 and go to 8. So either way, it wouldn't have mattered in which direction I counted. No matter what, it has to be an 8-methyl. Right, so putting all of that together, we end up with 8-methyl bicyclo, 3, 2, 1 octane. All right, let's go ahead and take a look at this one. And we know that this is a bicyclic compound with fused rings, right? So our parent is going to contain the word bicyclo. There will be 3 numbers inside of brackets. And then if I count this up, there's 6 carbons, so this is a hexane. Okay, what are the 3 numbers, right? So let me identify my bridgehead carbons. And then those are the paths that connect them, right? So we have a 3-carbon path, a 1-carbon path, and a 0-carbon path. This Okay, so 3, 1, 0 are the numbers in there. And there are not any substituents, right? So no substituents, right? So then this just becomes the name. The parent is also just the name of the compound. I believe that's the last slide for this section, and it is. So good luck with the activity and practicing your nomenclature.